Hello again. Welcome to the third lecture of week 3. What did we do last time? If you remember, I had introduced you to functional testing. How is functional testing done popularly? And we looked at various techniques of functional testing, an overview of functional testing. In that, one of the testing techniques was equivalence class partitioning. Today, I'd like to spend some time on that. We call equivalence class partitioning as input space partitioning because it involves partitioning the input domain. So it is practically the same as equivalence class partitioning. So I'll introduce you to that domain of equivalence class partitioning or input space partitioning in detail in today's. So we begin by understanding what are partitions of a set. So I'm given a set S. Set S could be a finite set, an infinite set, a countably finite set. We really don't worry about what kind of a set it is. I want to understand what the partitions of the set are. So a partition of a set is a collection of subsets of the set S. Here it's a collection of n subsets such that each subset is disjoint pairwise with the other one. That is, they are mutually disjoint. Si intersection Sj is empty. They don't have any elements in common. And put together the union of all the subsets, you get back the entire set. So that intuitively explains the word partition also, right? Partition means I take a set S, divide it into various subsets. The various subsets that I divide it into should satisfy a few properties. The number of subsets that I divide it into should be finite. In this case, it's n. Each of these subsets should not have anything in common with any other subset. That is, they should be pairwise disjoint. And put together, all the subsets together constitute the entire set S. Nothing is left out after partitioning the set S. So in this small figure here, the set S is partitioned into 4 partitions, S1, S2, S3 and S4. If you see, put together, these 4 partitions constitute the entire set and they are pairwise disjoint. So this small example will illustrate partitions work. Now, how are we going to use partitions as far as testing is concerned? So this set S that I defined for a partition of S, the set that we are going to partition is what is the input domain. So take a program. The program will have several inputs. All the inputs could be of various types. The input domain, as we discussed in the last lecture, constitutes all the types of the inputs that the program has along with the domain types as declared within the program. It can be thought of as a Cartesian product or a cross product of all the input types. For example, if a program has let's say 2 Boolean inputs and let's say 1 integer input, then the input domain will be the set 0, 1 for 1 Boolean input, cross producted with 0, 1 for the second Boolean input, cross producted with the domain of integers based on the kind of computer the program is going to run on. So that's the set that we're going to take and partition. Input domain, as I told you, can be several different sets, typically 1 for each input. While doing partitioning, we may or we may not consider all the inputs. Testers typically sometimes decide to focus only on certain inputs, don't consider all the inputs for partitioning. But when they are doing, let's say, integration level testing, they might consider all the inputs for partitioning. So it widely varies based on what is being tested and the tester's choice. It is believed that each partition of an input domain represents one property, or in the testing jargon, we call it characteristic. It represents one characteristic of the input domain, and the program that is being tested will behave in exactly identical way for any input value from each partition. So I take an input domain, partition it into several partitions, and pick one value to define my test case from each partition. And the belief is that the program behavior in terms of the expected output that the program is expected to produce will be exactly the same if I pick up any input from each partition. But inputs across partitions, the program is expected to behave differently because each partition represents a different characteristic. And there is an underlying equivalence relation. Equivalence relations are binary relations that satisfy certain properties. We are not interested in defining or understanding what they are, but equivalence here means that the behavior of the program is identical for any choice of input from a given partition. So we say that the set of partitions are the equivalence classes induced by an equivalence. So how do we define partitions and characteristics? Each partition, as I told you, is based on a characteristic or some property of an input domain. So here are some example properties or characteristics. You could be worried about a property which asks whether the input is null or not. You could be worried, let's say the input is a file, you could be worried about whether the file is in sorted order or not. And if it is in sorted order, what is the order of sorting? Is the file in sorted order? Is it in inverse sorted order? Or it's in arbitrary order? It's not sorted at all. So each characteristic allows the tester to define one partition. So we'll see a few examples that explain how to define additional characteristics. So what are we looking at? We're looking at two properties, as I told you. If you remember in the first slide, I told you what do partitions satisfy. They have to be pairwise disjoint and put together, they have to constitute the entire set. So when we look at characteristic, we are looking at characteristics. The partitions induced by the characteristics must cover the entire domain. Put together, they must cover the entire input domain. In testing terminology, we call it the partitions are complete or completeness property, and the disjointness should still hold. Partitions must never overlap. Every pair of partitions should be disjoint with the other one. So for example, if I consider the characteristic that I showed you in this slide, the order of a file, is it sorted, is it inverse sorted, or is it arbitrary? Here is one example of an attempt to define a characteristic and go ahead and look at partitions based on that characteristic. So I could say here are the three direct partitions. First partition could ask whether the file is sorted in ascending order. Second partition could be all files that are sorted in inverse ascending or descending order. Third partition could be all files that are not sorted, that is, they are in arbitrary order. But remember, if this is the partitioning and we want to go ahead and check whether these partitioning satisfy these properties or not. If the partitions don't satisfy the properties of completeness and disjoint, we don't work with them for testing at all. Because testing without these two properties can be considered to be have errors, it could have a lot of issues and problems. So partitions have to be complete, they have to be disjoint. So here for this example partition, is it complete? Is it disjoint? The problem is it is not disjoint. Why is it not disjoint? It's not disjoint because suppose I consider small files, that is files that have length 0 or length 1, then the file will be sorted ascending, the file will be sorted descending, and the file can be thought of as not being sorted at all. So such files that are of length 0 or length 1 will belong to all the three partitions, which means the disjointedness property is not satisfied. So what do? What we usually do is we consider the same characteristic, but not in exactly this way. We tweak it a little bit and write it slightly differently. So we write the characteristic of the order of the file as follows. We ask a question for the characteristic. So we ask, is the file sorted in descending order? Or is the file sorted in ascending order? The answer could be a yes, in which case it is true, and the answer could be a no, in which case it is false. So if I write the same thing like this, you will observe that the disjointedness problem goes away. How does it go away? Take a file of length 0 or length 1. So it will be sorted in ascending order. So it will belong to the true part of this partition. It will be sorted in descending order. So it will belong to the true part of the second partition. But the first characteristic, which is being sorted in ascending order, induces two partitions. Is it true? Is it false? And a file of length 0 or 1 belongs to exactly one of these. And the second characteristic, which is the characteristic of being sorted in descending order, induces two more partitions, true and false, and a file of length 0 or 1 again belongs to exactly one of these partitions. So we basically consider partitions the way intuition tells us, by looking at properties, by looking at specifications. But what I'm trying to tell you through this slide is that you have to be a little careful in way you write it. If you write it directly like this, sorted ascending, sorted descending, sorted arbitrary, then the partitions may not be valid. But if you consider each one individually and consider it as being true or false and being true or false, then the partitions satisfy the disjointedness and completeness property, so they are valid partitions. We'll move on to considering the input domain and how to model the input domain. What do we mean by modeling the input domain? Modeling the input domain means that I have to be able to understand which are the sets that constitute the input domain for my consideration to be testing now, and how do I go ahead and identify characteristics for these sets and partition them based on these characteristics. Typically, what do we do? Here are the steps that we undertake. The first step that we do is we identify testable functions. When is a function testable? If you remember in the last lecture, I had shown you an example of knowing the context, right? There was a large program P that was calling a particular function, right? So that function inside the program P was the function under test when we were doing input space partitioning or equivalence partitioning for that function. So in general, a program could have several different testable functions. So we now focus on which are the functions that we want to begin testing on. So that process is what is called identifying testable functions. So I begin by identifying which are the functions I want to test. So those are what are called testable functions. The second step is to identify all the parameters that can affect the behavior of a testable function. Like for example, if you remember in the previous lecture, that particular function f was called only when x was greater than 20. And that property was very important for that. I called it as testing the function in context. That's what this step is talking about. Once you identify all the parameters, these parameters put together constitute the input domain of the function that is being tested. Now, once I have the input domain, I have to be able to model it. Now, what do I do here? I look at the properties of the function under test. What do I want to test about this function that is under test? What are the requirements that this function is supposed to satisfy? What is its functionality? I look at all that. That will help me to identify characteristics. I take the characteristics and partition based on each characteristic. And what do I do for test inputs? I take one partition. I told you any set of input values representing that partition is good enough as a test input. And each test input should belong to exactly one block from each characteristic. And please remember, when I choose characteristics and partition based on the characteristics, partitions must satisfy the property of being disjoint and complete. So what are the two approaches of input domain modeling? There are two popular approaches to do input domain modeling. One is called interface-based approach, and the other one is called functionality-based approach. So we'll spend a few minutes understanding what each of these approaches are. And two things to be observed. While I model the input domain, I need to know the domain. What do I mean by need to know the domain? I need to know what the program is going to do. Let's say the program is a program that is going to fly an aircraft. I need to know a little bit about the application domain of the program. Let's say the program is a program that's supposed to be in a banking sector, then I need to know a little bit about the application domain. So I need domain knowledge, and my partition should consider both valid and invalid input because I am going to test the functionalities. So what we'll spend some time on now is what are these two approaches to model input domain modeling. So the first approach is what is called interface-based input domain modeling. So here what it does is that there are several characteristics of an input domain. There could be several parameters induced for each of these characteristics. Interface-based approach considers each characteristic or parameter in isolation. It considers it. What are the possible strengths of interface-based approach? Interface-based approach is supposed to make it easier to identify the characteristics because we really don't worry about how they influence each other, how one influences the other. And what are the weaknesses? The weaknesses are, the problem is typically not all information is available to the test engineer that will be reflected correctly in the interface domain model when we consider each characteristic separately. So there could be a risk of the input domain models that I consider. By models for input domain, I mean sets. The sets that I consider for input domain could be incomplete. And because I don't consider how they depend on each other, I might miss some functionality. What I am trying to do in interface-based approach is that I am trying to analyze each characteristic in isolation that might miss some functionalities that come as a part of combination. So we'll see examples that will help us to understand both the strengths and the weaknesses in detail. The next approach is functionality-based input domain modeling. In this method, characteristics are identified based on the overall functionality of a system. So let's say I have a program under test or a function under test. I look at what that program or the function is supposed to do. What is its main functionality? Why is it written? Why does it exist? I look at those characteristics and then consider partitions of the input domain based on characteristics that represent the functionality of the considered program or function. The strengths are that because I consider the main functionality, this approach is believed to yield better results than interface-based approach. In fact, there are empirical studies. I'll give you some references about empirical studies in input domain partitioning where this is validated. And since it's directly based on functionality or requirements, test case design can start very early in the development lifecycle. Remember, functionality caters to requirements, and requirements are the first thing that are baselined in a typical development of software. So a test engineer can start designing test cases right at the requirements phase without waiting for the program to be ready. Of course, for executing these test cases, you need the program to be ready, but for designing the test cases, I can start upfront. What are the weaknesses? The weaknesses are because it's directly based on functionality, you need domain knowledge, and identifying partitioning the input domain model can be non-trivial. So this is a small example. This is an example of a code which is supposed to take a list as an input along with an element. If you remember, we looked at this code once before in one of the earlier weeks, and it's supposed to find out whether this element is present in the list or not. If the element is present in the list, it will return true. That's why it's supposed to return a Boolean value. If it's not present in the list, it will return false. If the list itself or the element is null, then it will throw an exception, null pointer exception. Please remember, I have not given you the full code here. Why have we not given us the full code? We have not given the full code because, as I told you in the last lecture, our focus is black box testing. In black box testing, I don't design test cases based on the code. All the information that I need is, which is the program you want me to test? This is the program of find element. What are its inputs? Its inputs are list and the element to be found in the list. What is this program supposed to return? It's supposed to return a Boolean value, true or false. And when there are problems, it's supposed to return a null pointer exception. This is all the information that I need to know. I don't have to know the code for the program because I'm doing black box testing. With just this information, can I use input space partitioning to design test cases for the program? That's what we're going to look at. Now let's look at the characteristics for interface-based approach for this. What do I know? I know that this list, there's two inputs, list and an element, two possible outputs, true if the element is in the list, false if the element is not found in the list, and an exception. So a simple interface-based input domain partitioning will look like this. Is the list null? It will ask, and the answer will be true if it is null, false if it is not null. And then is the list empty? It will ask, answer will be true, answer will be false. You could go ahead and write a few more things. Is the list, is the element present in the list? But when we talk about is the element present in the list, we are not considering interface-based approach. Please remember that interface-based approach considers each parameter, input parameter, in isolation. For this program, there are two inputs, list and an element. So interface-based approach directly considers the list and considers partitions of the kind of list only. It doesn't ask a question about whether the second input, which is the element, is it there in the list or not. It doesn't ask that question. When we do functionality-based partitioning, we will consider that property into consideration. That's what we do here. So when I do functionality based approach for that list example, if you look at the bottom of this slide, we say, is the element present in the list? How many times is it present in the list? Number of occurrences of element in the list. If it is 0, which means the element is not present in the list. If it's 1, then it's present in the list exactly once. If it's more than 1, then it's present in the list more than once. So one characteristic based on which I derive the partitions is the number of occurrences of elements in the list. It doesn't occur, which is the first one. It occurs exactly once, which is the second one. It occurs more than once, which is the third one. Now, if you see, both the inputs to the program, the element and the list, are together considered in functionality-based approach. When we did interface-based approach, we considered only the list separately. So another characteristic that we could arrive this is just as an example for functionality based approach, is the following. We can ask, does the element occur first in the list? Not a very interesting characteristic, because the program is not worried about asking whether the element is occurring first in the list or not. But let's say I'm interested in this characteristic for some weird reason. Then I can again write it as saying, if it does occur first in the list, then one characteristic says true. If it does not occur first in the list, the next characteristic says false. So how do I do a functionality based approach? Where do I get these things from? Usually in a program, preconditions, post-conditions, they are very rich sources to understand functionality. For example, if you look here, right, it is just a small little comment that acts as preconditions on what the program is expected to do. So I don't really need the code of the program. Just by looking at this, I'm able to arrive at characteristics, right? The other things that people usually look for, testers usually look for while writing characteristics, is to look at implicit and explicit relationships between variables. I'll show you an example later in the lecture today about what this means. The other functionality people look for is typically what is missing functionality, so that they can identify if the program is correctly handling missing functionality. And just to stress it again, to do all this you need extensive domain knowledge. Domain knowledge, I mean the domain of this in which the software is running. So the next step is choosing partitions. How do I choose the partitions? As I told you, the number of partitions should not be too high. If you choose a very fine-grained characteristic, then you'll end up in too many partitions. And then if you choose one test input for each partition, there'll be too many test cases. Sometimes it might be needed to get clarity if error is very deep in the program, to get focus on the error. But in general, it involves an experienced balance between choosing the partitions wisely such that they are not too large in number, but at the same time very effective in finding faults if any. How do I identify values within partitions? Typically, partitions should be such that all these things are used to find the test input values. I should find a few valid values, means there should be, in that list example, there should be a nice long list and a case of element being present in the list at least once. And sometimes I might have to consider one partition in isolation and partition it further. There could be needs for that. Sometimes we have to identify values exactly at boundary. If you remember in the last lecture, I told you that once I do equivalence class partitioning, I can also do boundary value analysis. That's what this is about. And some partitions have to give me invalid values, because I need to know whether the program has exception handling features for all these things. And as I told you, there must be a balance between the number of partitions and effectiveness in finding test cases. And there should not be any missing partitions. I should get back the entire input domain. That's very important. It should be complete. And as I told you, there should not be any overlapping partitions. The partitions should be disjoint. So what we'll do for the rest of today's lecture is we'll take one example and we'll go through what are the various ways in which we can partition the input domain for that example. So the example that I have chosen is the example that we did when we did logic coverage criteria, because that was the most recent example that we visited. So I thought it would be fresh in your mind. So it's good to revisit that example. So the example that we did was the type of a triangle example, abbreviated as TriTyp. If you remember, we had this program in the last week where we looked at this TriTyp program, which took three sides of a triangle as input and determined what was the kind of triangle. Was it an equilateral triangle, isosceles triangle, or was it an invalid triangle, and so on. So here is an example of how an interface-based partition for that will look like. For example, I could say that there are three sides, side 1, side 2, side 3, and I could consider the relationship of the three sides to be with 0. So I could say, what is side 1? Is side 1 greater than 0? Is side 1 a number, length of side 1 a number equal to 0? Is length of side 1 a number less than 0? That could be one partition. The next partition could be the same thing for side 2. Is the length of side 2 a number greater than 0, equal to 0, less than 0? The next partition could be related to the same thing for side 3. Is the length of side 3 greater than 0, equal to 0, or less than 0? So suppose I consider partition Q1 for side 1. What do? I choose one value from each partition, which will result in 3 tests, right? One for side 1 greater than 0, like for example you could choose 7 or any number greater than 0 as the value. The second one says side 1 is equal to 0, that's what I've chosen as the second value. Third one, choose a negative number, side 1 less than 0. So if you see here, what do these two represent? Side 1 equal to 0 and side 1 minus 3, which is less than 0. They represent invalid values. So what do they test about the program? They test whether the program handles these invalid triangles correctly. So that also satisfies this condition that I told you here, that some partitions should include few invalid values. So another this is one partition which checked for greater than 0, equal to 0, less than 0. Sometimes you might want to refine it into doing 4 partitions. You might want to do greater than 0, equal to 0, separately maybe equal to 1 and less than 0. This is just a choice, just to give you an illustration of an alternative option to do partitioning. In this case, what will happen? There will be 4 test inputs. One for a side 1 greater than 0, one for side 1 equal to 0, one for side 1 equal to 1, and one for side 1 being a negative number. Similarly for side 2, similarly for side 3. Now, another subtle point that I would like you all to understand and observe here is that if you remember the program TriTyp, input to the program were 3 integers. If you remember, all the 3 input to the program were 3 sides, and all the 3 sides, what was their data type? They were all integers. These partitions are valid provided the 3 sides are integers. Suppose I make the 3 sides of the triangle as floating point numbers, then this way of doing partitioning is not valid. Why is it not valid? Because it will not be complete. If you see these 4 partitions, if they are floating point number, then between these 4 partitions, none of the partitions test for this length of a side of a triangle being a number between 0 and 1. Let's say the length of a side of a triangle is 0.7. It doesn't test for that. It doesn't belong to any of these partitions. So it doesn't satisfy the completeness criteria. But for that program that we had, our type of the 3 sides was integers. When I consider integers, these partitions are valid. So you have to be very careful in determining whether partition is valid or not. Based on the type of the domain, one partition could be valid for one domain type and could be invalid for another domain type. The same partition could be invalid for another domain type. So when I do functionality based partitioning of TriTyp, I don't directly look at inputs in isolation. I start looking at the functionality of the program. What was the program TriTyp supposed to do? It was supposed to determine the type of a triangle. What were the 4 types of outputs that it was supposed to produce? It was supposed to produce numbers as 0, 1, 2, 3 to tell you what the kind of triangle it was. It was supposed to tell you whether the triangle was scalene or isosceles or equilateral or invalid. So a functionality based approach will consider the functionality of a program. What is the main functionality of the program, and try to come up with a characteristic based on the functionality. In the case of type of a triangle, the functionality was the type of the triangle itself. So here is one partitioning. So I say my criteria for partitioning is the classification for the type of a triangle, and then there are 4 partitions. The triangle, the 3 sides are such that the triangle is scalene, the 3 sides are such that the triangle is isosceles, the 3 sides are such that the triangle is equilateral, and one of the sides or maybe more than one of the sides are such that the triangle is not a valid triangle. So suppose I consider a partitioning this way. Before we move on and design test cases, as I told you, the first thing to understand is, are partitions complete? Are partitions disjoint? You'll realize that these partitions are not disjoint. If you think for a minute, can you tell me why these partitions are not disjoint? What is the problem? The problem is, if you see, every equilateral triangle is also an isosceles triangle. What is an equilateral triangle? It means all the 3 sides are equal. What does isosceles triangle say? Any 2 sides are equal. So when all the 3 sides are equal, any 2 sides are equal. So this partition, suppose I give a triangle that is equilateral, it will belong to B3 partition and it will belong to B2 partition. So it doesn't satisfy the property of disjointedness. So how do I overcome this small issue? The tweak or the correction that I have to do for the partitions is very simple. So I just rewrite the partitions to mean that it's scalene, it's isosceles but not equilateral, it's equilateral, and it's an invalid triangle. What will this achieve? This will make sure that here for B2, I do get a triangle that's only isosceles. It will separate equilateral triangles that also have the scope for being isosceles. So it says isosceles triangle, not equilateral. This way, I made sure that the partitions B2 and B3, which were overlapping here, become disjoint here. Now I'm ready to give test inputs to start testing the program. So the test inputs that I could give are one set of test cases that will test whether the triangle is scalene. For example, 4, 5, 6. This is good enough to test if a triangle is scalene. It will be. This is another set of test cases with two sides being equal to test if a triangle is isosceles but not equilateral. The third set of test cases with all three sides equal. I have given 3, 3, 3. Give any values, all of them need to be the same. 4, 4, 4, 5, 5, 5. Anything is all right. This tests for equilateral triangles. This tests for not a valid triangle. Is this clear? So if you see throughout what we have done, we looked purely at the input, looked at what input values could be given and how they could be partitioned based on just the input values, which is interface-based approach, which was discussed here, or based on the overall functionality, which is a functionality-based approach, which was discussed here. So to design test cases for input domain partitioning, I don't really need the program code. I need knowledge about the inputs, and I need to know what the functionality of the program is, and I could partition the input domain in several different ways. What we'll do in the next lecture is we'll look at, once I have come up with the partitions, how do I design test cases? What are the various coverage criteria to design test cases? Do I pick one value from each partition? Do I pick one value from each partition such that every other value from other partition is covered? Do I pick two values from each partition? Is there one partition that I have to focus on? All these things we'll understand in the next lecture. Thank you.